First of all, please subscribe my channel and follow me for the future lectures. In this lecture, I want to talk a little about the numerical integration. Numerical integration. In fact, in lots of area of the science and engineering, for example, in physics, in mechanics, in electrical engineering, and some field like this, we need to compute a definite integral. We know that the definite integral is to form a integral from a to b, f of x d of x. This integral usually has a number as the solution or as the result. For example, when we say integral from 0 to 1 to x d of x, we know that by the main theorem of integration, this is x squared from 0 to 1, and this is 1 minus 0 and equal to 1. In fact, we know that the integral from a to b of f of x d of x is equal to f of x, okay, from a to b. This is the, in fact, the fundamental theorem of the integration, the definite integration. And we know that f of the big F of x is a function such that if we take a derivative of the big of f, it will be equal to f of x. But the problem is that in many cases, you cannot find the integration of f of x. In fact, you cannot find a function like f that if you take derivative of f, you find the little f of x. For example, suppose that we want to compute integral from 0 to p. E to power of minus x squared d of x. We know that there is no function, okay, that if we take derivative from that function, we get e to power of minus of x2. But we know that the value of this integral is the square root of p over 2. So the question is that how can we find this value without computing the, in fact, big F, or without taking integral from F? This is the problem. Or in some cases, for example, you want to compute the integration from p over 6 to p over 3 square root of tangent of x differential of x. We know that this integral can be computed, but it is very hard and very difficult to compute, and then using the fundamental theorem, okay? But we know that we can compute this integral without finding the in fact, the big F of x. This is the main, in fact, problem in this section. Now, in these cases, we can use some numerical method to find the value of the integral. So, if I want to write, I can write in these cases, we can use numerical integration. Okay, we have several different technique for the numerical integration. For example, we can use unknown coefficient, or we can use Newton-Cotes formula, or we can use Gaussian integration. We will explain all of these techniques in this course, and in fact I will describe all of these techniques, and I will tell you the advantage and disadvantage of each technique. The first one, let me start with the unknown coefficients. The main idea of the numerical integration is that we approximate the integrate, for example, integral from a to b f of x differential of x. We approximate it with a sigma, which it has some ai, and f of xi for I equal to, for example, 0 to n. Okay, this is the idea of a numerical integration formula. In these cases, we have to determine some things. Okay, first of all, we have to determine what are xi's, and then we have to compute ai's. Okay, so let me write. In this formula, we have to consider some xi from I0 to n as nodal points, and then compute ai for I equal to 0 to n as unknown coefficients. Okay, so in the first part, let me consider a partition for the interval of a and b. So let a and b has a partition like x0, this should be equal to a, less than x1, less than x2, and so on until xn, and this is equal to b. Okay, and let h be the difference between xi and xi minus 1, and also let the distance between each two neighbor xi's are have the equal distance. So just let me mention here xi's are equidistance. Okay, and also let f of xi be fi for I equal to 0, for I equal to 0 to n. For example, In the integral from, for example, 0 to p e to power of minus x squared, okay? So let me just, instead of p, let me put 1. There is no different, okay? Here, a is 0, b is 1, and we can consider, for example, 0 equal to x0 less than x1 equal to 0.25 less than x2 is equal to 0.5 less than x3 is 0. For example 75 and less than x4 equal to 1. So you can see that all of the xi's have the equal distances, okay? So this is the idea of this one. And also when I say f of fi, for example x0, this is f of 0, and we know that this is f of x, so we have to put 0 in this function, e to power of minus 0, and it will be 1, okay? And for example f of x1 is f of 0.25, this is e to power of minus 0.25 squared, and so on. So we can determine all of these values, okay? Now consider a numerical integration formula as integral from a to b f of x d of x b equal to sigma n equal to 0 or I equal to 0, yes, to n a I f I. This is equal to, for example, a 0 f0 plus a1 f1 and until an fn. Okay, this is a quadrature formula, in fact. Now we have to find a0 a1 to an, so we have to find a0 a1 to an. Okay, to this end, what can we do to this end? Let me start with a definition, and then I continue by some very special cases, and I find some very, very famous formula. Let me start with a definition. We say that a numerical integration formula is accurate up to order, for example, k. Okay, if the formula is accurate for polynomials from degree 0 to degree n. Okay, what does it mean? It means that if we have for example, a to b f of x d of x be equal to some I equal to from 0 to, for example, n. Okay, f I a or a I f I, something like this, a I f I. If this formula is accurate, for example, up of order 3, it means that if you put instead of f1, okay, this formula should be equal. If you put instead of f of x the function x, this formula should be accurate. Okay, and if you put, for example, for instead of f of x x squared, this formula should be accurate, and so on. Okay, now in a very special cases, consider that we have just one point in the interval. Case 1. Let me write something else. 1 point. Okay, so let me write something here. Let we have just a point, 1 point, 1 point, for example, x0 in the interval, and f of x0 be known. So we should have the numerical integration as follow: a to b f of x d of x be equal to alpha 0, for example, f0. We have f0 equal to fx0, and we have to find alpha 0. Okay, but this formula is accurate of order 0. Okay, so this formula should be accurate for the polynomial of order 0. So let me write this formula should be accurate of order 0. So it should be accurate for f of x equal to 1. Right? So let me put it. A to b 1 d of x should be alpha 0, and we know that if f of x be equal to 1, so f0 also should be 1. So it should be times 1. And this means that alpha 0 be equal to b minus a. Okay? So the integration formula is integral a to b f of x d of x be equal to b minus a, we put it instead of alpha 0, times f0. Okay, this formula is called rectangular integrating formula. Rectangular formula. Okay, rectangular formula. Why we call this formula rectangular formula? Because if, for example, you have a function like this, I have this plot for the functions. Okay, let me plot something like this. Okay, and consider, for example, here as A, here as B, and consider x0 here. Okay, now if you find this point is f of x0. Okay, and consider from here to here, this is b minus a. If you times b minus a times f of x0, which is this, in fact, you can find something like this. Something like this. In fact, you find this area, okay? This area, and this is in fact a rectangular with the length of b minus a and the width f of x0. Okay, so this is the rectangular formula, which is an approximation for the area under the curve between a and b, x equal to a, x equal to b, and x axis. Okay, this is the simplest integration formula that we can find. But if we want to have a little, in fact, more accurate and a little more complex technique, we have to consider 2 points in the interval a and b. For example, a as the first point, x0, and b as the end point, we call it x1. So let me consider case 2, and let me consider 2 points. Which points? x0 and f of x0, x1 and f of x1. For the simplicity, usually we consider x0 equal to a and x1 equal to b. Okay, now consider the integral from a to b. F of x, d of x, b equal to alpha 0, f0 plus alpha 1, f1. This formula should be accurate for the polynomial up to degree 1. Okay, so this formula should be accurate for polynomials up to degree 1. Okay, so it should be accurate for f of x equal to 1, and this get a to b, 1 d of x, b equal to alpha 0. And we know that if f of x be equal to 0, f0, in fact, or f of a should be 1. So it should be times 1 plus alpha 1 times 1. And this gives alpha 0 plus alpha 1, b equal to b minus a. Right? And also we know that if it should be in fact accurate for the polynomial of order 1, we consider degree 1. We consider f of x be equal to x as the a polynomial of the first degree. So integral a from a to b, and you put instead of x here f of x, put x, d of x b equal to, and here alpha 0, put alpha 0, and here instead of f put x. Okay, so if we consider f of a, it should be a. Okay, so alpha 0 a plus alpha 1 b, and this means that alpha 0 a, or we can write a alpha 0, maybe it's better, a alpha 0 plus b alpha 1, and here this integral is half x squared from a to b, and it will be half times b squared minus a squared. Okay, so in fact we get a system of equations like this. Okay, if you solve this system of equations, you can solve it easily. It's not difficult because we have two unknown with two equations. It's just enough you delete one of these unknowns and find the other one. If you solve this equation, you will get alpha 0 b equal to alpha 1 b equal to b minus a over 2. So finally we get a new formula for the numerical integration. So in fact we have for a from to b f of x d of x, b equal to b minus a over 2 times f0 plus f1, and in fact we know that we have some error here. This is in fact error. Okay, and if I want to do not write this e, I can omit d and change this equality to almost equal. Almost equal. Okay, now if we consider, if we put b minus a b equal to h, so integral from a to b of f of x d of x, this is almost equal h over 2 times f0 plus f1. Look at here, I delete e and I change equality to almost equal. Okay, this formula is a new formula for computing the, in fact, integral. If I plot a diagram for this formula, I can find something. Let me do it. Let me consider y-axis and x-axis, and also let me consider a function, for example this function, something like this, and also consider a and b as 2 points. Let me consider here a and here b. Okay, this point is f of b and this point is f of a. Okay, what I have computed here. Look at here, from here to here is h. This is h. Okay, we add f0 plus f1 and multiplied it by h half. It means that this is exactly the area of a trapezoid here, this trapezoid. Okay, in fact I have approximated the area under the curve y equal to f of x, lines x equal to a and x equal to b, and the x axis by the area of a trapezoid. So this numerical integration formula called trapezoidal formula. Okay, this is the trapezoidal formula. Now let me continue the lecture in the next lecture, and let me just ask you for subscribe on my channel, and please watch my videos online as you can. Follow me and wait for the next lecture. Thank you.